Okay, Matt Roscoe here for our last video lecture in Math 595-50, Teaching Geometry from a Problem-Solving Perspective. Um, this week, I'd like to just wrap up by talking about the three different geometries and how they come into play in problem-solving settings. So, a quick overview. We'll just review what the three geometries are: synthetic, analytic, and transformational geometries, and then I'll make a quick statement about how I believe that the three geometries are usually never used exclusively in problem-solving settings, but rather um, play a role in, supporting one another in constructing solutions, and hopefully give you some evidence through some examples. So, we can just review where we've been in K-12 mathematics. We can loosely categorize instructions into three different perspectives in which mathematical objects are visualized, and the perspectives are synthetic geometry, analytic geometry, and transformational geometry. Synthetic geometry, sometimes called axiomatic or pure geometry, is the study of shape using an axiomatic method that begins with a set of givens, these are axioms, and builds results, usually theorems or lemmas or corollaries, using only the tools of logic and tools to draw points, lines, and circles, the primitive elements. So this would be a compass and of course, synthetic geometry is the place we're heading to in high school, and is usually the major, feature of high school geometry is the synthetic proving part. So transformational geometry is the study of shape understood according to the size and shape-preserving actions of reflection, rotation, and translation, as well as the shape-preserving action of dilation. So this would be this idea of symmetries being studied and looking at the isometric transformations, reflection, rotation, translation, and the non-isometric transformation, the one that changes size, which we call dilation. Oh, did I miss one? Oh, sorry, I did miss one. Analytic geometry is sometimes called Cartesian geometry or coordinate geometry, and it's the study of shape drawn on a coordinate system. So here's the broad statement I wish to make, and I guess try to substantiate in a couple examples, is that when students are presented with what I would think of as authentic problem-solving settings, the three geometries often serve as resources in the problem-solving process. So the results that we have in the three geometries, of course, are the tools that we can bring to bear on a problem when we're faced with not knowing what to do, which is what I think authentic problem-solving is. And while some problem-solving prompts require the application of mathematical tools from only one of the three perspectives we've explored, it's perhaps more common that two or more of the perspectives are helpful in the construction of a solution. So these are what I would like to call rich geometry problem-solving opportunities when you have to coordinate between, let's say, two or three perspectives that are commonly taught in the K-12 curriculum. So let me give you some examples of what I mean by this, and I'm going to draw all the examples as well as the homework on the content side this week from problems chosen from the middle school math competition known as Math Counts. I'll make this a resource as well for you in your final problem-solving activity this week, but I just think it's an excellent resource for problems that are rich problem-solving opportunities. And because it's written for middle school and at various levels of middle school students, some of which in 8th grade are already taking a high school geometry course, I find that the problems that come out of Math Counts are pretty appropriate for high school age students in the first or second year of study in what would be thought of as maybe a traditional geometry course. So we'll see what you think once you take a look at the problems I've chosen, and you're invited to elect a problem from Math Counts to be included in your last problem-solving activity in the problem-solving portfolio, so you can read about that on the web page. So here's the first example. You're given a square that has sides of length 4 units each. A stripe of width 1 unit is drawn inside the square, centered on the diagonal. The area of this stripe can be expressed in the form a plus b root 2 square units, where a and b are rational numbers. What's the value of a plus b? Express your answer as a decimal to the nearest tenth. Okay, well, so definitely a problem-solving setting. I can't think of any formula that I can directly apply or any procedure that I can directly apply, so I'm going to have to sort of think about what to do and apply some tools that I know from the 3 different geometries that we've studied. So let's go ahead and switch over to an overhead and start talking a little bit about how we might attack this problem. Okay, well, I think the first thing to note is that, um, maybe draw a little picture of this. I'm going to draw the square here over to the right, I guess. Something like this. We have a square, a little strip down the middle that's been painted white, I guess. We want to know the area of that strip. Really, the only thing that we're told about this is a few measurements. So we're told that that distance right there is 1 inch, or 1 unit, I guess. And we're told that the side length of the square is 4 units. So this is a 4 by 4. So I guess all of these are 4 in total length. It's a square, so I guess we know that these are all right angles. And the question is what's the area of that white strip? Well, right away when I look at this problem, I think to myself, okay, I can definitely see a line of symmetry in the problem. The line of symmetry, of course, goes through here. So I could kind of reduce the complexity of the problem, maybe by a factor of 1/2, by just analyzing half of the figure instead of sort of doing both sides. So that's what I'm going to choose to do. I'm going to redraw just half the figure. I'm going to find half of this area and then reason using symmetry that since the stripe is drawn along centered on the diagonal, I can reason using symmetry then what the area of the stripe is by just multiplying my result for half the figure by 2. So I'm going to draw a bigger picture of this now, so something like this, and start diving in. Maybe something like that. Okay, so what do we know? We know then that this is a right angle. We know that this whole distance here is 4. We know that this whole distance here is 4. So if it's a right angle and it's a 4 by 4, I guess the triangle we have drawn is isosceles, so we can conclude then using a little bit of synthetic geometry, I guess, that the base angles of an isosceles triangle are congruent. The sum of the angles in the triangle is 180, so if we take the 90 away and divide it by 2, then we know that both of these are 45s. So these angles are all 45. And we also know some results from Pythagoras, and that's a synthetic result. And the synthetic result will tell us the length of the diagonal if we want to know it. But what we're really after here is the area of this, I guess, shaded region here, right? So I'm going to label some of these points just so I can talk about it a little bit more effectively. So I'm going to call this A, this B, this C, this D, and this is E. And I'm going to reason that, to find the shaded area, I could find the area of triangle ACE and subtract away the area of triangle BCD. And so if I could find the area of both of those triangles, then the difference in their area should be the shaded region. So let's think a little bit about what we need to find the area. It seems pretty clear that triangle ACE, I can find the area right now. It's 1/2 4 times 4. But it's going to be a little bit more difficult to find the area of BCD because I don't know this distance here. I know it's 4 units minus whatever that little distance is right there. So maybe the way to think about it is to think about, well, what happens in this little corner right here is perhaps important for me to know. So if I drew a line perpendicular to the diagonal here, um, and try to figure out, I guess, what the hypotenuse, I guess, of that little right triangle would be. So let's call this little point here at A, B, C, D, E. Let's call that F, and let's draw up a kind of an exploded version of that triangle. 1, 2, 3, 1, 2, 3. Something that looks like this. So this is sort of an exploded version of that. So A, F, B. Now, once again, we know since this is an isosceles right triangle that that angle's got to be 45. We've chosen to construct it so that it's perpendicular, I guess, to this distance or this diagonal FE. We know that since the distance is 1 unit perpendicular to the diagonal, when it's cut in half, then that this distance will be half a unit. We also know that since this is a right triangle with a 45-degree angle, then this one will have to be 45, which means that one's got to be half as well. And that's enough for me to be able to figure out what this little distance is right here. So what is that little distance? We'll call it x. So we can say that 1/2 squared plus 1/2 squared equals x squared. So that's 1/4 and 1/4, so 1/2 is equal to x squared. If I take the square root of that, then I get x equal to 1 over root 2, which if I rationalize, if you like to do that, that would be root 2 over 2. So that little distance there is root 2 over 2. And so that allows me then to find out what the distance from B to C is, right? And I think that's all we need now to carry out the analysis that we proposed. So let's go ahead and do it. So let's find first the area of triangle ACE. Well, that's just going to be 1/2 the base, which is 4, times the height, which is 4. That's 1/2 of 16. So that's going to be 8 units squared. And let's see, let's try to find then the area of triangle BCD. There we're going to have 1/2 the base, which is going to be this distance 4 minus that little distance, which we've said is square root of 2 over 2. So it'll be 4 minus root 2 over 2. And the height, of course, by symmetry will be the same. This is an isosceles right triangle, so it's got to have two sides that are congruent. 4 minus root 2 over 2. So let's see, it's 1/2. 4 times 4 is 16. Root 2 times 4 is divided by 2 is just going to be minus 2 root 2. And the insides will be the same thing, minus 2 root 2. And then the last will be negative times negative or positive. Root 2 times root 2 is just a 2. 2 on the bottom times a 2 on the bottom, of course, is a 4. So how does this simplify out? Well, let's see. We're going to get 16 plus 1/2. So it's 16 and 1/2. That's this first and last term. Then we got minus 2, 4 root 2. That whole thing is being multiplied by 1/2. So I'm going to write this improperly, 32 33/2. So 33/2 becomes 33/4, and 4 divided by 2 becomes 2, so minus 2 root 2. Okay, so that is the area of triangle BCD. So that's BCD, this littler one here. We would assume that number is less than 8 because the larger triangle is 8, the smaller one should be a little less than 8. Let's just check it to get some intuition. 33 divided by 4 is 8.25 minus 2 times the square root of 2 Yeah, so it's about 5.42-ish. 5.42. So we can see already the answer, at least for this half strip, is going to be somewhere in the neighborhood of 2.5-ish. But let's go ahead and carry it through. So we would say then that the area of, I don't need of, I'm going to do the area of this shaded region here. So I'm going to call it, it's a trapezoid, so AEDB. AEDB is going to be, well, it's going to be the area of the larger triangle. So that's the area of triangle, sorry, ACE, minus the area of the unshaded part, BCD. Let's see, so that is going to be equal to, well, we said this was 8. Oh, I should have units squared. I forgot to put units there. So 8 minus 33/4 minus 2 root 2 units squared. Now it's a matter of just simplifying. So 8 times 4 is 32. So this is 32/4 minus 33/4. Negative times a negative will yield a positive 2 root 2. So it looks like we get minus 1/4 plus 2 root 2 as the area of the half strip, right? We got to be a little careful here, right? Because the way that we started out is we found the area of just that half strip, but we want, of course, the area of the whole strip. So, so the area of the whole strip is 2 times this value, right? Negative 1/4 plus 2 root 2. Oh, and this should also be units squared. So negative quarter times 2 is going to be negative half. 2 times 2 is going to be 4 root 2. And so that's the area of the whole strip. I guess the answer that math counts wants, of course, is the sum of the 4 and the 1/2. So the answer that math counts wants is 4 minus a half, or 3.5 units. Well, I guess it's not units at that point. They just want to know what a plus b is. So 3.5 is the sum of the a and the b written in the problem. So I guess looking back on the problem, it seems like this is, this is classic problem solving, and I would argue that we're seeing all three of the geometries. Well, it's really two geometries being particularly accentuated here. Certainly, we're using symmetry to argue that if we find, if we cut this thing in half and we solve half the problem, then the reflection across that line and symmetry across the diagonal allows us to just multiply our preliminary answer by 2 to get a full answer for the strip. I think the rest of it is primarily synthetic geometry. We're using synthetic results like the Pythagorean theorem, the fact that base angles of an isosceles triangle produce congruent sides and vice versa. Pythagorean theorem is used again, well, I guess just once here. And then we're just doing simple addition on areas to make, to find the area of half of the strip, and then again scaling by a factor of 2 using a symmetry argument to find the area of the whole strip. So I think it's pretty firm evidence that oftentimes when we are faced with a problem solving activity, that usually more than one of the perspectives in geometry comes to bear. I think this is kind of one of the things that makes problem solving in geometry particularly difficult, because geometry is often taught where all the problems come out of one of the perspectives, and rarely do students, well, I shouldn't say rarely, but perhaps less common is it for students to be faced with a problem where they have to access tools from more than just, let's say, the chapter we've been studying, such as what's going on here. Okay, let's move on and take a look. I'll call this example 1, and I'll make sure that that's copied into the notes. Let's go ahead and take a look at another example. Okay, so we did that one. Here's example 2. Circle O has a radius 10 units. Point P is on radius OQ, and OP is 6 units. How many different chords containing P, including the diameter, have integer lengths? Okay, take a second to just read that. Maybe sketch a quick picture. How many different chords containing P, including the diameter, have integer lengths?